for the writers program. The echo gone? Okay, someone me.
Oh, yes.
Yeah. Okay, great. Great. There we go. Can we all hear me online? Great. I got some quick questions just now in person, and I might as well show the answer to with the entire class. Students here in person, got a donut, got some napkins and a plate. So the question I just got was about what do people who are learning Python or trying to do research in AI do for like their access to Python and for code? Do they use Google Colab? Do they do something else? The answer to which is usually people would just install Python locally, try to get a working Jupyter notebook set up on their computers, and then use free software or free packages like PyTorch or maybe TensorFlow for some different functionality. Um, we're using Google Colab because it's easy to set up. Otherwise, we would have spent probably an hour or maybe even 2 hours making sure everyone had the installation working on all of your machines, which would have been quite time consuming. So Google Colab is just because its utility is quick. Um, so any other questions? Maybe some quick questions. Oh, I can do some mine. Great. Okay, so I think Yvonne, you said you wanted to give the introduction today for our speaker. I don't really have any major administrative announcements, except just that those who are attending in person or planning to be in person for the last day of our program, start thinking about what project or what brief presentation you might want to talk about. What I'll do is on probably Monday next week, I'll ask you to tell me something about some idea that you're hoping to talk about. Just try and think of something you can talk about maybe 5 minutes related to the class about data analysis or something interesting about the physics that you saw. Figure something out, think about it, let me know. Next Monday, I'll come around with a spreadsheet and ask you guys, and we'll work out some schedule for presenting, just sort of a what you learned very briefly on the last day of class. And we'll try and get some pizza or something again on that day and invite your parents so there'll be a party around associated with it. Okay, sound good, guys? No objections. I see nods. We're motivated by food, I see. Okay. Okay, Yvonne, go for it.
Okay, first of all, before I introduce Anna, just a quick thing. Somebody asked a while ago if there were any online resources that were good for learning Python. There's not an official Python for Physics recommendation. We haven't discussed it, but I found like 2 days ago this website called Code Wars, and it was really cool. It has like a leveling up system, and you can do like little exercises on Python that have to do with like handling strings, and they go, yes. Okay.
It's called Replit.
Replit?
Yeah.
Okay.
It's an on. The only thing is they've now started to make it harder for free users, but you can still learn.
Okay. It's always money. Okay.
Repeat that for them.
Yes, for the online audience, the student here was mentioning Replit, R-E-P-L-E-T, L-I-T, Replit, R-E-P-L-I-T. Oh, because REPL is the interface that you push code through. Oh, got it. Anyways, okay, let's get started. So it's my pleasure to introduce Anna Coerver, who's going to be our speaker today, and is also going to teach Python for Physics. Anna is a local here of the Bay Area. She grew up in Oakland, went to Oakland Tech, did her undergrad in physics at Barnard College in New York, and then came back here to do her PhD in physics here at UC Berkeley. And she's going to tell you about some really exciting research that she has done. Well, on the Big Bang, on the cosmic microwave background, but most importantly, in really cool places. So take it away.
Thank you, Ivana. Yeah, I'm Anna. I am a 6th-year PhD student here now, so I've been here for a while, and I work on an experiment called the South Pole Telescope, which is, as you might expect, a telescope at the South Pole in Antarctica. This is a picture of this beautiful telescope in the Antarctic winter, so you can see some auroras here behind it. And I'm going to start out with just talking about why we do research in Antarctica, the logistics of doing research in Antarctica, what other kinds of science go on down there, just kind of an overview to what life is like there. And then I'll go into some more details about the South Pole Telescope specifically and the kind of stuff that I work on. Yeah.
Can I make a quick announcement?
Yeah.
So for this, you're gonna use your laptops, which means, as I tell my students, that all my classes, you can put them away. And no devices or anything, just enjoy.
And also forgot grab donuts.
Yeah, grab those. Alright.
Sweet, thanks. Yeah, so I was at the South Pole for about 3 months last year. And that was a really amazing experience to be able to actually work on this giant telescope in person. So I'm going to start out just talking about that, and feel free to interrupt with any questions. For the people moderating online, if there's any questions that you think should be asked, like not at the end, feel free to interrupt me. I'm happy to answer them. Okay, so just a reminder of where Antarctica is. It's at the bottom of the world right here. We've got the Antarctic Circle and the Arctic Circle at the top. This entire line down here is the South Pole, because this is as if you've unfolded a globe. And another reminder, this is a question I get a lot, is did you see any polar bears? No, I did not. Polar bears live at the North Pole. At the South Pole, I did see penguins and seals that eat penguins. Antarctica is a really big continent. It's larger than the US, and it is not inhabited by humans, at least in like an indigenous way. Now we have scientific bases there, but it's generally not hospitable to life. There is some life around the coast of the continent, but in the center, you truly will find absolutely nothing, like not even bugs. It is the most desolate place on Earth. Okay, quick game of 2 truths and a lie. The South Pole is higher elevation than Mount Kilimanjaro. The South Pole is a desert, and the South Pole only has 1 sunset a year. So think about that for a second. Which one do you think is the lie? Raise your hand if it's number 1. Raise your hand if you think it's number 2. Raise your hand if you think it's number 3. Okay, mixed answers. That's fun. It is in fact number 1. The South Pole is at about 10,000 feet of elevation, which is high, but is lower than Mount Kilimanjaro's 19,000 feet of elevation. And at the South Pole, almost all of that is ice. So there is a land mass underneath the ice, but there's about 9,000 feet of ice. So that elevation is really just accumulation of snow and ice over time. The South Pole is a desert. This is true. Because it's too cold to rain, the South Pole has very, very little water vapor, which is a key reason that we do research there. It's considered to be the driest desert in the world. And the South Pole only has 1 sunset a year. This is also true. I'm going to talk a little bit more about this, but the South Pole only has 1 sunrise and 1 sunset a year, and each one lasts for weeks. You can imagine, you know, your normal day, your 24-hour day spread out over the course of a year. That's what it's like there.
I have a question.
Yeah.
But have you ever been to South Pole?
Yeah, I was there last year. You're going to see photos.
Yeah. You seen that you saw penguin, right?
Yes.
Wait, what? Does it snow in South Pole?
Kind of. I'll talk about it. Okay, so this is the weird things line, the Antarctic Circle. This is where you stop getting your normal 365 days a year and start getting a bunch of really strange stuff going on. And this is because of Earth's orbit around the sun. So Earth is on a tilted axis. It's not straight up and down. So it's on a tilted axis and it moves around the sun like this. So for half of the year, the South Pole is pointed towards the sun, and for half of the year, the North Pole is pointed towards the sun. And for the other half of the year, either pole doesn't get any sun at all. So you can see that for the winter, down here at the South Pole, you get constant nighttime, so 24 hours of darkness a day. And then in the summer, when the pole is pointed towards the sun all the time, you get 24 hours of sunlight a day. It's very weird. It's very trippy to be there. It definitely throws off your sleep schedule. And I'm just going to show a quick video of kind of how how the sky moves there. This one was taken in the winter time, so it's dark. And you can see, this is the moon here, not the sun, but you can see that it's just moving straight across the sky, level with the horizon. It doesn't rise and set like it does here. It just goes around in a circle all the time. And then these green and red things are auroras from solar winds and magnetic fields. That's my telescope. So yeah, pretty tricky, right?
Oh, how long the video, the 2 hours?
Yeah, this is a time lapse. It's that much movement. Yeah, that's probably 4 hours or so. 3 hours, 4 hours. Okay, so what's the process of actually getting down to the South Pole? You start out in New Zealand getting your gear issued. So they give us these really, really warm coats. This is about a $3,000 coat. It is ridiculously warm, which is awesome. And we don't get to keep it, which is a bummer. And then they also give you these insulated boots that are also super warm. And then they give you base layers, stuff to cover your face. Generally, if you're going to be outside for a long time, you don't want to have any skin showing. So this is the trip from New Zealand to the coast of Antarctica. I'm going to kind of go through the different legs of this. So yeah, we fly from San Francisco to New Zealand, and then you fly from New Zealand to this little bay right here, which is the closest point of Antarctica to New Zealand. And how we do that is we go on these US Air Force cargo planes. So they load up a bunch of cargo into the center, building materials, food, scientific cargo for experiments that are happening in Antarctica. And then we all, as the humans, get strapped into these like netted seats on the side. And because Antarctica is under the Antarctic Treaty, it is a peaceful continent, which means no weapons are allowed, no environmental contamination. It's a like a preserved continent essentially. So it's meant to really stay as a space for scientific research only, which is super cool. It's the only place like that in the world. But what this means is the military can't bring weapons. So these planes are specifically for Antarctic mobility. They have skis on the bottom so that they can land on the ice. And even though it is operated by the Air Force, there are no weapons on the planes. The soldiers don't carry any weapons.
What is the food service like?
No food service, but you can buy merch if you want.
How do you go to that? Like, how long is this flight?
Great question. The flight from New Zealand to the coast is it's 6 hours to 9 hours, depending on what kind of plane you get. There is a bathroom. It's basically a bucket with a curtain around it. It's like a little nice, like it's technically a toilet, but yeah, that's kind of the deal. So yeah, you don't want to do that if you don't have to. And you can also see there's not really windows. You're kind of just in this box. And it's really loud. So you bring noise canceling headphones.
Why is the box so loud?
It's just not meant for like commercial air travel is like comfortized, and that's not the point of these planes. So there's no, this is,
I feel bad.
they've maximized the interior space that's usable. And so there's not, I don't know, they're not prioritizing like sound insulation or anything like that. Okay, so when you land on the coast of Antarctica, this is what it looks like. This is the plane from the outside, you can see. And this is actually not land. This is the ocean. So because it's so cold there, you get a very, very thick sheet of ice frozen over the bay. And it's thick enough that for most of the summer, planes can land on it with no problem. It gets a little bit squishy towards the end of the season, but the airplane field is just the bay because that's the flattest space we have available. And you can kind of see the skis on the bottom of the plane here. So they have like bulldozer type things that go and compact the snow for planes to land on. But other than that, you don't really need a runway. Okay, so this is McMurdo Station. This is not the station I was living at, but it's the station I had to transit through to get to the South Pole Station. And it's on this island here called Ross Island. It doesn't feel like an island because the water's frozen over and you can walk on it, but it is technically an island. And right here in the center, we have Mount Erebus. This is Mount Erebus. It is the southernmost active volcano in the world, and you can see smoke coming out of the top of it. So that was pretty cool to be living right next to that.
What erupts?
It doesn't really erupt. Like it smokes like that all the time, but I don't think there's been a recent eruption. Yeah. Mount Erebus is pretty cool because it's a volcano that's in such a cold location, it creates a special type of crystal called Erebus crystals that can only be found in like one other location in the world. So there are these little rocks all over. There are these special types of like lava crystals that the volcano spews out. It's very cool. And I say that to just mention some of the other science that goes on at this base. So this is McMurdo Station. This is a big station. At the peak of summer, it has about 1,000 people. In the dark winter, there's about 150 people. But in the peak of summer, when scientists are coming in and out, people are doing biology on penguins and the sea lions and doing all sorts of glaciology, marine biology, all sorts of things. This is kind of turns into a little village. So this is fuel storage. You can see there's construction. Over here is dorms and dining hall. So it's kind of a pretty big ecosystem considering it's the biggest station in Antarctica.
The town.
It's a town, yeah. And then I also just wanted to show at the end of the summer with some of the ice melted, so you can kind of see that we actually are on an island. You can see that the ice starts to melt and you're like, oh wait, that's the ocean. Kind of cool. And I just wanted to quickly show some of the other science that goes on this space. This is an ice core. So it's a column of ice drilled out from a kilometer or so beneath the surface. And they do this to do essentially carbon mapping. So they can use the like little bubbles of trapped air in these cores of ice to measure the carbon dioxide on Earth at that time. And so they have really precise carbon measurements dating back to like 4 million years ago, I think. So that's one very cool thing that goes on. There's all this drilling and stuff for this. This is an experiment called GUSTO. It is a astrophysics balloon experiment, which means it launches up into the upper atmosphere of the Earth and orbits for a little while before coming back down. It's kind of halfway between a ground-based telescope and an actual satellite that goes into space. And this is for understanding the evolution and formation of galaxies. So it was very cool to be able to see this payload before it was launched and to talk to the scientists working on that. This is a NASA experiment. NASA has a balloon launching facility at this base. And then there's also a lot of marine biology. This is my favorite thing that I saw. They actually keep a touch tank for other scientists to come and poke at things. And this is an Antarctic sea slug type thing that had expelled its stomach to eat. I just thought that was very cool.
Expelled its stomach to eat.
Yeah, so that white thing, that's like its stomach. So usually that's inside and it like
So bring the food in.
it goes out and grabs it and brings it. Yeah. Yeah, there was some crazy stuff. They had these giant Antarctic sea spiders that were like this big that live deep in the ocean. Yeah, very cool stuff. And then you can also hike around the coast. There's a lot of really beautiful, calling them trails is a little bit generous, but there's some beautiful routes that people have gone through and checked for glacier crevasses or anything and flagged them so that you know that they're safe. So there's a few designated routes that you're allowed to walk around on. And I just think it's the most beautiful place I've ever been. Like, it's just amazing to be there and see just this massive expanse of white. So these are me and my colleagues taking some hikes around the island.
What time of year?
This was in November. Yeah, so northern winter is southern summer. So I went down at the beginning of November and I came back in February. And then just to show you the reality of hiking on a leave no trace continent, you do have to bring a pee bottle. Okay, so this is where I was, and then I took another one of those cargo planes to the geographic South Pole. It's called the Amundsen Scott South Pole Station. And you can also see on this map all of the other countries that have bases in Antarctica. So you can see that the US has these two right here, and we're right next to the New Zealand base called Scott Base. There's some Russian bases. You've got Japan right there, China, Germany, France. Yeah, anyway, there's, I think, a total of 33 Antarctic bases. And generally, countries don't share bases, but there is some amount of international collaboration in terms of flying in and out or sharing fuel. So that's pretty cool. Okay, back onto a cargo plane. This one was even smaller. We were really stuffed in there like sardines, but this flight was only 3 hours. So that was great. And this is some of the views from the plane. You can just kind of see what it looks like to fly over the continent. There's kind of nothing. It's just a lot of snow.
This one didn't have one.
This had, these are taken through, it was a window about this big in the back of the plane. And I just kind of sat there for the whole flight. The funny thing about flying in these cargo planes is you don't have to stay seated. There's no requirement that you're buckled in or like sitting in your chair. So I spent the whole time wandering around, standing at the window. You can lie down on the floor, take a nap if you want. It's very, very laid back.
Should you not fuck up?
Wait, I don't understand. How do you not get depressed if it's all just snow?
I didn't mind it. Some people definitely don't like it. Some people are like, get me home. I want to see trees. There's no trees on the continent. There's no plants on the continent. I thought it was beautiful. I thought it felt like being on another planet. It was very dramatic. The sun isn't setting. Like you're in this giant ice desert. It was such a unique and novel experience that it really, I didn't have a chance to be sad about the lack of trees, you know? Like it was just, I thought it was very special.
Oh, so cool.
Yeah, yeah, you kind of are, there's a lot of adrenaline.
How about the penguin?
The penguins are cool. I have some penguin photos that I can show at the end. Okay, so this is the geographic South Pole. There's a little sign here. This is the pole marker. The ice sheet moves a few meters a year, so you have to update the geographic South Pole location every year. This is the base that I lived in. It's this one big metal building. And unlike McMurdo, which you saw that was kind of a town, at the South Pole, it's just this. It's all of us in this one metal building, and there's nothing else except the science experiments. And this is what it looks like there. So at McMurdo, you had, you know, a little bit of wildlife, some mountains, some water, a volcano. But because the South Pole has had ice accumulating on top of it for millions and millions of years without ever melting, because it never gets above freezing, so the snow and the ice never has a chance to melt. You know, 9,000, 10,000 feet of ice just sort of flattens out the landscape. So, you know, like you're standing on this ice and 9,000 feet below you, there are mountains, but there's no trace of them anymore. So the entire landscape just looks like this. This is all there is to see. As far as I can see, it looks like this for hundreds of miles in every direction. It's about, I think, 600 miles before you get to the closest mountain. So that was pretty trippy. It really is like a true desert. And this is a couple of rooms inside the base that I like to show just because people are like, don't you get depressed? This is the craft room. There's a lot of art supplies, there's sewing machines. We had a lot of fun, you know, having movie nights or like themed nights. People would like make outfits or make crafts, decorate spaces. We do have a hydroponic greenhouse. Hydroponic means that there's no soil involved, only water and nutrients. We are not allowed to have soil on the continent, but we can grow things from seed in an isolated environment. It's interesting. It's very interesting to grow things without soil. There's certain battles that you fight that you don't expect to. And this isn't really a food source. Like you don't go down expecting to have fresh food. Pretty much everything you're eating is frozen or dehydrated or canned. But by the end of the season, we had managed to grow a good amount of like salad greens. We had a few tomatoes, some snap peas, and that was like a nice little treat to like have something fresh. Yeah. Because it has the potential to contaminate the continent. So you don't want to bring in anything living that isn't native. Obviously, if you put something outside in Antarctica, it wouldn't survive. But just in terms of scientific research, you want to preserve the continent as well as humanly possible. So when people are making measurements of the ice and the atmosphere, it's all accurate to, you know, the actual conditions. You don't want to bring in, you know, soil from California that kind of messes up the science that you're doing. Okay, so moving on to my actual research. This is the South Pole Telescope. It has a dish of about 10 meters across. And this is the team that I was with when I was down there last year. The whole telescope is about 75 feet tall. So it's quite the experiment. So there's a couple more photos you can see from the side here. This is the dish from the back. This is where all the wiring that controls the telescope runs through. This is also wiring here. And up in here is the actual detection hardware, which I'll show in a second. So this is not, you might look at this and go, this doesn't really look like a telescope. I'm used to like seeing something that you like look through and it's got a lens at the end and you're like looking through it and you're pointing at something in space. That's because we are not looking at visible light. We are looking at millimeter wave light, which is not visible to the human eye, but contains a ton of information about the early universe. So in order to detect millimeter wave light instead of visible light, you need to use specific technology, including basically a giant radio dish and a bunch of unique focusing optics and a very unique detection system.
Like the right picture, you're sliding.
Oh, this is, I call this telescope sunbathing. So the temperatures at the South Pole, while I was there only in the summer, and they ranged from -50 to -15 or so. But if you sit right under the telescope dish, it focuses a lot of sunlight and you can actually take off your jacket and be comfortable in a t-shirt. It like heats up this one little area. So sometimes we would sit in the corner and telescope sunbathe. Yeah.
When you say that this camera is like your typical telescope where it has a lens and it's trying to detect things you can't see, is this what like the near infrared cameras look like?
Yeah, it's very similar. So infrared and millimeter wave are next to each other on the electromagnetic spectrum. And I'll show a diagram of that in a second. But yeah, it's very similar.
So the James Webb has something similar to this?
It is pretty similar. Yeah. So it's different. It requires different detection technology to detect infrared versus millimeter. And the James Webb is also interested in a different type of source. So like we're looking at leftover light from the Big Bang, which I'll get into more detail about. James Webb is trying to map, like sources in the sky generally and like gas and stuff. So the actual like focusing optics and what you want your resolution of your telescope to be are different. So this is much lower resolution than James Webb because we're not looking for stars specifically. But yeah, great question. Okay, so this is the inside of like the telescope guts. We call this big metal thing here a cryostat. And we call it that because it's a chamber for cryogenically cooling the optics and the detectors. So even though we're in Antarctica and everything is freezing already, we actually need our detectors to operate at about 300 millikelvin, which is, if you are familiar with Kelvin, ridiculously close to absolute zero. And if you're not familiar with Kelvin, that's about -450 degrees Fahrenheit. So that's a lot colder than the air temperature of Antarctica. So we have this giant cooling chamber. Inside of that, this is our focal plane. All these little holes are essentially guiding the light onto our detectors. So you can think of them as kind of like a funnel for light, guiding the light down to the detectors. And then we have underneath all of these very sensitive electronics that detect the millimeter wave photons. Any questions about that? That was a lot of words. Cool.
Different kind of question.
Yeah.
And how do you generate the electricity to use?
Yeah, great question. So it is all generated from fuel. And every summer, there's a team of about 15 people that drive tractors that drag giant fuel bladders for 800 miles from the coast to the South Pole. It takes them about a month to drive there. And they do this trip 3 times over the course of the summer in order for us to have enough fuel to operate through the winter.
This is all covered, who paid for the research, and I guess part of that research fund goes into the kind of part of the fuel.
Yeah, so everything is funded by the National Science Foundation. The National Science Foundation has a sub-branch called the Office of Polar Programs. And the government both provides funding for all of this to happen, but also contracts out to private companies. So for example, a lot of the personnel who aren't scientists are hired by private companies that go out and find the people to do, you know, plumbing, electric work, cooking, washing dishes, cleaning, all of that stuff. And they do the hires and the personnel for that. And so the National Science Foundation isn't directly overseeing people who aren't scientists. So it's kind of like a multi-tiered organization, but it is all funded by the federal government. Yeah.
Why can't the scientists cook the food?
We could. It's easier to not put people who aren't trained in charge of a large kitchen. For example, at McMurdo, you've got 1,000 people. If 1,000 people were all trying to cook their dinner every night, that would be really, really difficult. So it's a lot easier to have a dedicated team of people making 3 meals a day and then everyone else just coming and grabbing. It's like the most efficient way to do it, right? Like it's pretty inefficient to have 1,000 people using ingredients in a not efficient way in a place where food is very valuable because it's hard to get it down there. Costs a lot to bring food down there. You're pretty limited in what you have. Things are generally shipped in huge bulk quantities. So it's much easier to have dedicated people cooking.
Another question is like the sleeping accommodations. How do you guys do that?
Yeah, so there's basically dormitories. So you have a room in a hallway. It's very small. It's about, let's see, room was probably about this wide. It's a twin bed. You have a little bit of space to walk. You have a closet. That's it. And then you share a bathroom. And then at the South Pole, everyone there, we have people cooking, but we like clean the station ourselves because it's a much smaller station. So you do shifts for cleaning the bathrooms and washing dishes and all of that stuff. But yeah, it's pretty communal. Okay, why did we put a telescope in one of the most remote places on Earth? Probably one of your takeaways is that doing all this is really difficult and costs a lot of money. Yeah, question?
I don't know.
One sec. Oh, for responses? Sure, go ahead. Yes, yeah. Yeah, that's definitely one of the reasons. Did you want to also?
Is it because the pole is facing, so like it's much easier to like see like the different points?
Yeah, that's also one of the reasons. So you just mentioned this one. So because it's dark for 6 months straight and the sky never changes, we can point in the same place year round. We're never going to get a different part of the sky. So we can make the highest quality maps of that area of the sky as possible.
Got under 2 decades.
The main reason is that it's a desert. So in the millimeter waves, there's another word for millimeter waves. Does anyone know it? Something you're familiar with? Microwaves. Yeah. So think about your microwave at home. In order for something to heat up, what does it need? What does it have in it? Water. Yeah. So microwaves react a lot with water. So if we were in a place where there were tons of clouds all the time, tons of water vapor, we would have the microwaves that we're wanting to detect being hugely contaminated by all of that water vapor microwaves. So being in the driest desert in the world is really the #1 reason for being at the South Pole. There's no other atmosphere like it anywhere in the world. In addition, it's a high elevation, which means the atmosphere is thin. That's also better for observing, just less molecules between us and what we're trying to see. Yeah. Yeah.
I'm wondering, would it be okay if we took a little minute to just answer some questions that?
Yeah. Yeah.
Let me just maybe see some, like, for example, are there any microbes?
No.
Everything does. Do you get cellular services?
No. So you mentioned not having other kind of waves interfering with our observing, and that's definitely a benefit from being down there. Because we're vaguely in the radio regime, our electronics will detect things like the 2.4 gigahertz Wi-Fi line. And so at the South Pole, it's great that there's not, tons of Wi-Fi and Bluetooth everywhere. We do have Wi-Fi on the station for about 6 hours a day when a satellite passes overhead. Other than that, no internet. And we have basically the telescope is placed about a mile away from the station, and that's far enough to not strongly detect the Wi-Fi from the station. But whenever we go out to the telescope or anyone else comes out to the telescope, we make everyone, put their phones on airplane mode, turn off their Wi-Fi, turn off their Bluetooth, turn off their personal radio, which is how we communicate on base since we don't have Wi-Fi most of the time, because all of that will show up in our electronics.
And just one, because I'm very interested, the last one, how do you get to study in Antarctica? Like, what are some of the pathways that people use to get there?
Yeah, so I guess that question could either mean how does one end up in this kind of a position, or what are the different kinds of science that you could do that could get you to Antarctica? Which I can answer both.
Right.
I think in terms of the science that you can do that gets you to Antarctica, there's kind of everything. I mean, obviously climate science and environmental science is a huge one. There's a lot, I would say probably the most scientists in Antarctica are studying glaciers, subglacial lakes, microbes in subglacial lakes. I guess when the person who asked about microbes, there's nothing living at the South Pole, but around the coast there it gets warm enough that you can have kind of little organisms and stuff in like melted bodies of water underneath ice and stuff like that. You can do astrophysics, either balloon launches at the NASA facility. You can do astrophysics at the South Pole. There's a particle physics experiment at the South Pole that studies neutrinos, which we'll talk about in the Python for Physics lesson today. And yeah, that's pretty much it. You can also go through the NOAA. What does NOAA stand for? National Oceanic and Atmospheric, or something like that. That's a branch of the government that's separate from the National Science Foundation and is actually, I think, housed within the military that does atmospheric monitoring. Yeah, so those are kind of some of the science things that people do in Antarctica. How does one actually get to Antarctica? So either you become a scientist in one of these areas, which I didn't go into physics seeking this out. I went into physics, being really interested in astrophysics, looking for astrophysics research. And then after I had gotten into Berkeley for grad school and I was talking to the professors I was interested in, I knew that I wanted to move into cosmology and the study of the early universe. And I really loved this South Pole Telescope experiment. And, I'm the kind of person that really wants to go on these sorts of weird and slightly uncomfortable adventures. So that was just an additional plus for me in joining this lab. But I didn't, I wasn't like 16 being like, I'm going to find a way to get to Antarctica. It was something that kind of became an interest later in life. Okay. Okay, what does the universe look like? The internet will tell you the universe looks like this. The internet is wrong. Just kidding. I mean, the universe does look like this with certain telescopes, but for the purposes of this presentation, the universe looks like this. So what is this? This is a uniform photon field. We call this the cosmic microwave background. The Big Bang happened everywhere, right? So in the very early universe, we think that there was this huge explosion. The universe expanded very, very rapidly. That expansion slowed down. We finally got, first atoms, first molecules. But there was so much energy contained in the early universe that energy ended up distributed evenly everywhere. It wasn't an asymmetric explosion where you like have some jet shooting off in one direction. So what we get is a radiation field that is uniform across the entire universe. And that is the wavelength that I'm interested in and the wavelength that my telescope studies. And that's why to us, the universe looks like this. Obviously, there's some like stars and stuff in there too, but this is the important thing. Okay, so this uniform background of light occurs here, which is invisible to humans. You mentioned the infrared earlier, right there. So we can only see this tiny chunk of the electromagnetic spectrum, but there's so much in this direction and so much in that direction, and all of that contains unique information about the universe. different kinds of stellar explosions end up over here, and different kinds of magnetic fields end up over here. So really, if you zero in on any tiny piece of the spectrum, you get a totally different view on the universe. Okay, so how can this be true? The answer is the Big Bang. The people who originally discovered this actually thought that there was pigeon poop on their antenna because they were getting this constant static all the time. And they were like, something has to be wrong. They went up, they're like, oh, there's all these pigeons living near our experiment. They've all pooped on the antenna. They clean off the antenna, they still see that static. And that's when they realized, oh, this might actually be the signal that we've been looking for from the universe. This is a true story. They won the Nobel Prize. So 14 billion years is a long time to travel. We think the Big Bang happened about 14 billion years ago. So this light originally was extremely high energy, but over the past 14 billion years, it's been making its way to us here on Earth, and it gets stretched out. And that's why we've ended up in this low energy regime over here. Okay, so let's zoom in. Here we have the Big Bang, and this was the first inflation of the universe, where the universe expands very, very rapidly and to an extreme amount in a very short period of time. This line right here is 10 to the negative 32 seconds. So this happened incredibly quickly. And the amount of energy in that explosion, we think, was about 10 to the 16 giga electron volts, or 10 with 25 zeros, the number of fireworks. If that gives you a better sense of how much energy this was. Okay, so after inflation ends, we get quarks and gluons globbing together, and we get the first formation of atoms like protons, particles like protons. The reason that this says protons formed instead of protons and neutrons formed, because everyone knows that, right, that our atoms are made up of protons and neutrons, is because neutrons, I'm foreshadowing our Python for Physics lecture, neutrons are unstable. If they're left alone, they're going to decay into protons. And so we did end up with some neutrons because some of them were bound up into atoms with protons before they could decay. But we only ended up with 1 neutron for every 6 protons. So this was really the universe was mostly protons at this point, and electrons. We get nuclear fusion, which means that the protons and neutrons were fused into hydrogen and helium. Those are the elements that existed in the early universe. A little bit of lithium, a little bit of beryllium, but really mostly hydrogen and helium. Nuclear fusion ends. We now have some atoms. We've got this radiation field and these atoms, and the universe is finally cooling down enough that light can travel in a straight line without getting hit at every moment. So that's when we see the formation of this uniform background, the cosmic microwave background, because in here, obviously there's still radiation, but because the universe is so dense, everything's intercepting each other all the time. So we say that the cosmic microwave background formed at 380,000 years after the Big Bang, when radiation was finally allowed to move through the universe uninterrupted. Any questions there? Okay, and then the universe goes through a period that we call the Dark Ages, where everything has kind of globbed into its atoms, but we don't yet have the first stars and galaxies. Things collapse into the first stars and galaxies. They start emitting their own radiation, like starlight, and that's how we get to the modern universe we have today. So obviously a very simplified explanation. If you want to learn more about this era of the universe, I'm going to show a link at the end with a tutorial that I think is just an amazing explanation of the science behind all of this. Yeah, okay, so this is the point where light stops getting bounced around. So I said that the universe looks like this. It's a little bit of an oversimplification. The temperature of this radiation background is about 3 Kelvin. But if you zoom into microkelvin scales, it actually looks like this. So if you really zoom into these tiny variations in the temperature, it looks splotchy. But we get a ton of science from these splotches. This is actually where all of the information is hidden. So a map like this can answer, is space-time flat? What kinds of particles and fields existed in the early universe? Is the universe expanding or contracting? What kind of matter makes up the universe? So huge questions that we can get just from these maps that we make, just incredible. And you can kind of build this standard cosmological model. The CMB, the cosmic microwave background, has been one of the most powerful tools of our generation in building up our understanding of the universe and making these kinds of huge measurements. We can turn these maps into what we call a power spectrum. So this is power, like intensity of the light, versus scale on the sky. So like if you look up at the sky, are you looking at small scales? Are you looking at large scales? That's what this plot is. And if you look at kind of the variations across scales on the sky of these tiny temperature fluctuations, you can learn about the curvature of the universe, the matter density in the universe, dark matter, and a lot more. So that's just a little peek into how we actually do this early universe science and where these results are coming from. And that's kind of all I have to say about cosmology because we are running out of time. But do people want to ask any questions about the science before I move on to other things?
There were questions about how do you get things so cold in your experiment?
Oh, yeah, great question. So there's a few types of cryogenic systems. Generally, they take advantage of the I'm trying to think of which one to talk about. I'll talk about the newest version. The newest version that is relevant for this generation, no one's going to use anything else anymore, is the kind of cooling system that we'll be deploying in about 2 or 3 years, and that's going to become the new cooling system for my telescope for the next decade or so. It takes advantage of the thermodynamic properties of helium-3 and helium-4. So helium-4 is your typical helium that you like fill balloons up with. You can buy it at the store. Helium-3 is a much rarer, more valuable isotope of helium. And they have very interesting thermodynamic properties where if you mix them, cool them to certain temperatures, allow it to boil off, allow it to separate, they go through like this superfluid transition. It's pretty complicated thermodynamics, but essentially you mix these two gases together, they do crazy stuff, and then they pull entropy out of the system. I think that's kind of the best I can do without going too in depth. Anything else?
There's so many questions.
Wait, do atoms worth money?
I don't know how to answer that.
Do atoms what?
Do they worth money?
Depends what atom.
Worth money. The word you use, like, worth money.
Like, can you buy an atom? Depends what atom. But
No.
in bulk.
People have been paying for gold for a little while.
Okay, we'll do more questions at the end with like whatever time we have left. So I'm just gonna quickly talk about what a career in physics can look like. I just gave you the hyper-specific story of my personal career in physics, but a physics degree can turn into a lot of different things. Physics covers a huge range of science from astrophysics to materials science, tiniest particles possible, quantum mechanics, quantum computing, physical chemistry, scientific computing, metamaterials, biophysics, all sorts of stuff.
I'm not sure about quantum computing.
I don't know if I can answer it, but go ahead.
If you have questions about quantum computing, you want to give a talk a little while, and Dave would be happy to talk about quantum computing. So.
Yeah, that's really nice.
A physics college education generally includes physics and math classes, coding, some lab-based classes, and usually some research component. I got into physics because I had a professor encourage me to start doing research early on in my college career, and I really fell in love with it, and so I kept seeking out research opportunities. But it can also result in, industry internships and all sorts of other things. And a physics career can include components of research, engineering, coding, writing, pen and paper math on the more theory side. And I just kind of made this list of this kind of careers that people I know have after getting a physics degree, just to show that people go in a ton of different directions with this. So I'm a scientific researcher, and people in this room are scientific researchers. role as a professor, obviously. But people also end up doing software engineering, teaching, being data analysts, working in finance, renewable energy. I have a friend who works in patent law as like the physicist who understands patents. People do science communication, science policy, medical physics, a whole range of stuff. And so some of my work looks like this. This is kind of the stuff that you guys saw, which is, the inside of a telescope. This is at one of the national labs here in the US. But a lot of my work looks like this, making histograms like you guys made on Monday and like we're going to make today, coding, looking at plots, trying to figure out what's going on. And I'll end with a picture of some penguins, and I can take any more questions.
You study how, like, in the early phases of the cosmic microwave background being made, how the radiation of that affects like the early black holes, the early galaxy formations.
Yeah, so I specifically focus on the inflationary period of the early universe. So trying to detect a signal of the gravitational waves that we predict existed in that period. There definitely are a lot of people who study that transition to first galaxies, first black holes, and there's so much work to be done there. It's very hard to look that far back in time. The cosmic microwave background is pretty unique in that we actually have access to a period of time very far from us, and we can use it as sort of a backlight. So it kind of shines behind all of the other stuff in the universe, and we can detect things that way. But it's very hard to just point a telescope and see something that existed, 10 billion years ago. So that's a super active area of research that definitely requires like a lot of technological development. Yeah.
How the accuracy of what the data you get from the telescope is being verified?
Great question. So this experiment, COBE, is credited with taking the first cosmic microwave background temperature variation data. And you can see how nice those maps were back then. This was in 1980 something, in the 1980s. WMAP was its predecessor. You get a little better. Planck is the current only CMB satellite experiment. So Planck is orbiting Earth out in space, so it has really, really beautiful data. It takes slightly different data than my telescope takes. So Planck is amazing, like way out here. And we're a little bit better on the larger angular scales. But Planck maps were kind of the thing to beat for a long time in terms of the cosmological precision. And I will say that cosmology experiments have gotten incredibly precise. Like we are gathering so much data and we're getting such small error bars. And the reason that that's so exciting is we can compare our cosmological measurements with those from experiments that aren't looking at the cosmic microwave background and look at discrepancies and figure out what we might be missing in our standard model of the universe and its evolution. And there definitely are discrepancies. If this is something you're interested in, there's work to be done. There's so much we don't know. So much we don't know. So this is a satellite experiment. All these were satellite experiments. Ground-based telescopes, like the one that I work on, are just starting to surpass the sensitivity of this experiment on certain scales and under certain conditions. So basically we are getting more and more precise with time, but we are now limited not by technology, but by funding. So the way to get more precise measurements is to build just way more telescopes. Like if you made an array of 20 of the South Pole telescope, you would get such incredible precise data, but these telescopes are very expensive to make. So at this point, our detectors are as sensitive as you can get them. They're what we call photon noise limited, which means that their strongest source of noise is statistical fluctuations of photons, which is a quantum source of noise that we can't reduce any further. So in terms of detectors, we are as good as we can possibly get. And now we just are trying to bring down the statistical uncertainty by building more telescopes. So yeah, funding limited, not technology limited. Yeah.
The Planck was better at some types of data measurements. What would it be better at? Like, where would you use it?
So Planck gets very, very good measurements at small angular scales. Basically, the way telescopes work is the bigger the telescope, the better the angular resolution. But because Planck is a satellite, it can't have a 10-meter dish like we have. So we actually, on like the very smallest angular scales, we do better than Planck. So like if you go out, if you go out to the end of the spectrum, because Planck is just, it's launched into space, so it can't be 10 meters across. It just is physically limited and it can't do as well. But because it doesn't have, atmospheric noise, water vapor noise, it still can't be beat, on the scales that don't require a large dish. That makes sense. Yeah.
Why are early universe gravitational waves so important?
So we have this theory of the Big Bang and early universe inflation. The strongest evidence we have for the Big Bang is the cosmic microwave background. We have no other ideas of how something could make just this uniform radiation field everywhere in the universe. Like that really supports the idea of the Big Bang. But we still are not certain how the universe got to the state and the size that it is today. So we think that it had this like super rapid early universe inflation because that's the only way that we've been able to explain certain properties of the universe, like how big it is right now and how flat it is. But we don't have direct evidence for this. We only have indirect evidence. And what that means is we can't actually probe, if there was inflation, we can't probe like what were the fields that drove inflation? What was their value? What were the kinds of particle fields that might have existed then? So I'm working towards getting a actual detection of the fields that would have existed during inflation. And that would give us, instead of indirect evidence, that would give us direct evidence. Like that would be a Nobel Prize. That's like one of the things in cosmology that people have been trying to get at for 30 years because physics kind of, often the way physics works is there's a theory and you're working towards that theory, you prove the theory, and then the theory goes into like the canon of like, okay, this is what we understand about the way things work. And inflation is still just a theory. We haven't quite reached the threshold of like, okay, this happened this way. We have direct evidence. So that's why it's important.
And is LIGO likely to be able to detect those gravitational waves in a regional time scale comparable to you guys?
So detecting them as a gravitational wave background is definitely something that LIGO is working towards, but that honestly, I couldn't tell you which one's harder. Like it's such a small amplitude on both sides. Like the hope originally in cosmology was that these fields would leave like a noticeable and large signal in the cosmic microwave background. And under certain models of inflation, that would be true. And as we've gotten more and more sensitive, we've ruled out certain models of inflation that people previously thought were likely because we haven't seen something, we haven't seen something, we haven't seen something. So the line is moving down, and with it, all these models are getting ruled out. And so LIGO it doesn't really work the same way. Like it would be really amazing if they were actually able to detect this background, but they're not. Like the CMB, I think is special because you're able to actually systematically work through the model space and the parameter space. And even if we don't detect something, we're ruling out all sorts of scenarios. So, but yeah, I don't really have a good answer for like, will they do it? I have no idea.
Somebody can ask this question to Vicky Chu on Friday, because she works at LIGO.
Yeah, someone should ask her. Yeah.
What are the remaining models of the Big Bang like?
So the leading model, I don't know that it's actually the leading model. It's the most well-studied model, and it's the simplest model. So we kind of, in physics, we like to go with the simplest thing first, and then if that proves to not be true, we add complications. It's called slow roll inflation, and it basically imagines the inflationary field rolling down a kind of slope of potential energy, and by kind of rolling through this potential energy space, it creates these space-time fluctuations. Trying to think about how to explain this. There's some models that create different shapes of that roll, like the energy field has a different shape, I guess I could say. There's also models that add like a space-time curvature component to the Einstein equations and actually modify gravity to make it happen. It's a very complex theoretical like model space. There's some crazier things like people inventing various particles that could have a field that does something. There's a theory that has to do with the Higgs particle being involved, which you guys learned. The Higgs was mentioned on Monday, I think. But yeah, the kind of like simplest one is this like you have a field of potential energy, and the inflationary field is kind of like rolling down this hill of potential energy. I don't know if that means anything to you. That's all I got.
Alright.
Cool.
Well, if there's no more questions, why don't we thank Anna one more time? And we can take a quick break, then get back to Python physics.
Yep. Okay, everyone online, we are going to take a break, and then we're going to start the Python for Physics lecture.
You know, like, have you ever touched a penguin?
Okay, so the question that I'm about to answer is what percent of computational versus what percent of experimental work? That was the question?
Yeah.
It really varies depending on your interests and who you are as a person and what you want to do. My PhD has been something like 80% computational. So I've been much more on the, science analysis side of the data than on the building things side. I'm getting more into the building things side and I'm very excited about that. But yeah, some people do their PhDs, the reverse, 80% hardware, 20% analysis. But yeah, that's my personal split. Yeah.
People land all year round? And can people go to
Oh,
all year round?
That's a good question. So no, the South Pole base, you can only land from October to February. And then during the other 7, 8 months of the year, it is too cold for any machinery to operate. If the plane were to land, it would freeze and not be able to take back off. So yeah, if you go down there for the 8 months of winter, you are stuck there. No matter how bad the emergency, you are not getting out. You're just there. So you're trapped. Yeah, it's a pretty unique experience. I have a lot of friends who have done it, and have enjoyed it, but it definitely is, a high intensity thing to be there in the winter. It's dark the whole time. I mean, the friends that I have that have gone, obviously you're there to work on the telescope and to keep it operating. So you do have something to do. You're not just sitting in the darkness. You've got friends. There's about 40 people on base in the winter, so it's not that many, but there are people. And I think it's a very specific type of person that wants to do that. You don't choose to do that unless you think you're capable of it. And there's also, advantages, for example, seeing the purest, darkest, most beautiful night sky in the world. There's no better night sky possible. So people want to see that. They want to see the southern lights, the auroras. Yeah. But yeah, it's intense. Okay, we're gonna move on to Python for physics now. Hope everyone enjoyed the little research jump for a bit. And today we're going to be talking about data analysis and the neutrino mass and neutrons. Kind of mentioned earlier that we were going to talk a little bit about neutrons and neutrinos. So let's get into it. This shouldn't be super long. You guys have already heard me talk a lot today. And the project, I think, should also be relatively quick. So yeah, let's get started. This is kind of recap from last week. We're doing some intro to data analysis, some intro to particle physics and relativity. Can anybody tell me the 4 fundamental forces? Yes. All right. These are the 4 fundamental forces: gravitational, electromagnetic, strong nuclear, and weak nuclear. Today, we are going to be focusing on the weak nuclear force. There are 17 fundamental particles that describe essentially everything, and these are made up of fermions and bosons. We have quarks, leptons, a whole bunch of particle jargon that you don't need to worry about. We are going to be focusing on basically the idea of the proton, the neutron, and the neutrino. So quantum chromodynamics tells us that the proton and the neutron are made up of quarks. You can see these little circles inside each of them. Each one's made up of 3 quarks. Atomic nuclei are composed of these protons and neutrons. For example, carbon-12, the basis of life, is made up of 6 protons and 6 neutrons. So these interact and are bound together by the strong nuclear force. And the proton and neutron are made of quarks and gluons, which also interact via the strong nuclear force. So the strong nuclear force is what's kind of like gluing everything together. There's also a theorized particle called a gluon that actually does the gluing.
Has it been proved that it exists?
No, it has not. Well, actually, what do we think? Well, I guess it depends what you mean by prove it exists and what it means to really exist. Like, is there a strong force field? Like, in practice, yes. Would I consider the gluon like a studied particle? No. Okay. So as I mentioned earlier, neutrons are unstable. When isolated, they decay. They undergo something called beta decay. Here we end up with a proton, a lepton, and a neutrino type particle. And physicists are able to study this kind of particle decay by using the properties of energy and momentum. So can anyone tell me what is special about energy and momentum? They're conserved. Yes, that is the main point of today. Energy and momentum are conserved, and this is super useful for particle physicists. Okay, so if a particle is moving at some speed v and it has mass m, it has a momentum of p equals mv. A lot of you guys might have learned this in your intro physics classes already. The speed v is the change in distance over the change in time, delta x over delta t. And this Newtonian mechanics form of the momentum comes from the low energy approximation of this more complex version of the momentum, where we have mv over root 1 minus v squared over c squared. So what this tells us is that if the particle is moving at a much, much slower speed than the speed of light, this is essentially zero, and you just get 1 minus 0 equals 1, square root of 1 is 1, and this just simplifies to p equals mv. If the particle is moving close to the speed of light, then you need to use this formula to correctly calculate its momentum. And generally, to make things easier, we work in units where we set the speed of light c equal to 1. Are there any questions I should answer in the chat so far that are relevant? Cool. You can okay, units are made up, right? Like units are a convenience to be able to calculate things correctly. And we say, like, how do we define a pound? You know, like we just all agree that a pound is what it is. If you work through all of your calculations, setting the speed of light to 1, you know that that's the units that you've worked in, it's completely fine. You just have to know that at the end, whatever you come up with, that's the units that you worked in. And this is kind of a convention in general relativity to make calculations easier because the reason this makes things easier is you're probably familiar with the famous equation of E equals mc squared. So this is kind of the fundamental energy of something with mass. If you set c to 1, then you can use energy and mass interchangeably, which in general relativity is very useful. For you, not that useful, but if you were calculating, you know, space-time curvature, it would be very useful. But yes, it is uncomfortable, and often people will also set, you know, the Planck constant equal to 1, gravitational constant equal to 1, everything equals to 1, and you basically just come out. It allows you to basically get rid of all of the constants, add them back in at the end if you want, you know, the correct, some kind of specific unit, and just do the algebra without them. Yeah. Okay, so if a particle is moving, then it also carries energy. Einstein taught us that the energy of a particle is related to its momentum via the square root of mass squared plus momentum squared. And this is kind of a somewhat equivalent form of that. Okay, so all physicists agree that energy and momentum are conserved in a reaction in nature. When physicists first realized that neutrons decay, what they saw was this. And that really freaked them out because that would mean that energy and momentum is not conserved. And so people were wondering if the fundamental laws of physics were being broken. And then Wolfgang Pauli proposed the existence of a neutrino, a close to massless particle that would still carry momentum, to solve this problem. And it turned out that he was correct. There is a particle that exists that we call a neutrino, and it turns out that energy is conserved. Phew, don't have to worry about it. So neutrinos have no charge, very tiny masses, and barely interact with other matter, but they are detectable. There's a lot of physics experiments in the world that are working on studying neutrinos, both directly and indirectly. Some of those are IceCube, Dune, Super Kamiokande. So yeah, we're studying neutrinos in detail now. It's no longer just a theorized particle. And it solves this problem of energy and momentum are still conserved, and we can trust the laws of physics once again. The reason this energy and momentum conservation is so useful for particle physics experiments is you can basically do what I was talking about here with beta decay for any number of particle collisions. So at CERN, the Large Hadron Collider in Switzerland that Ken was talking about last week, you have these giant particle tracking solenoid type things. These are huge. A person is probably, let's see, like this big on here. These are really, really big. And this is kind of what particle tracking software in one of these experiments would detect. You create some collision, and then you measure the energy and momentum of all of the things that get created, and you kind of track that back to reconstruct what actually happened in that collision and to try to detect new particles, understand particles better, things like that. Okay, so if a system of particles with energy E and momentum P goes through a reaction and it has this final energy E sub F and P sub F, we expect those to be equal. So here's some, like in CERN, you have some collision or some explosion, but you expect the starting value and the ending value of both energy and momentum to be equal. And if you prove this to be wrong, you would definitely get a Nobel Prize. So feel free to get started on that. Okay, for project number 4, we are going to be calculating a particle decay to 2 particles. So we're going to start with 1 particle with a mass of 2. Choose whatever units you like. When it's at rest, it has momentum of 0, and it decays to 2 other particles. 1 particle we're going to call MB, and we're going to give it a mass of 1. And we're going to give this other particle MC an unknown mass. And your job is going to calculate, given a distribution of momenta, the distribution of masses that you measure. So for a little bit of algebra, we can solve for this quantity MC in terms of the things that we know, which is the mass of the original particle, the mass of the second particle in the post-explosion or collision or whatever, and then the momenta of this known particle B, which you are going to be given a data file for. So we've done this algebra for you. If you get bored and you finish the project early, you're welcome to work through it on your own. You could even try to do it with 3 particles instead of 2, see how that works out. So you're going to want to determine the mean value and the standard deviation of the particle MC given the measured values of the momentum of particle B. Does that make sense? So this equation is here for you. The files that you need are in this drive, Python Physics Materials for Students, day number 4. You're going to use a text file that looks like this. You're going to load it in. You have 1,000 measurements of the momentum of particle B. I've given you a notebook that has some kind of like fill in the blank structure to create these histograms. I know that you guys learned how to make histograms last week, so hopefully this will just build on that. And you want to start by plotting a histogram of these momentum measurements, P sub B. And then you're going to want to eventually get a histogram of the unknown mass, N sub C, and see how well you can determine the mass of that unknown particle. Any questions? All right, let's get started, and I'll be around to help if needed. For the folks online, the lecture is now over. We're just going to be working on the project for the rest of the day today, which we have about half an hour left.
Missing on Friday for the, what's it called? The, but I'll pause my histogram. So can you quickly like show me how to do it?
Yeah, I'll show you that in a second. So you can go and get the notebooks from Friday also in the drive, and you can look at the solutions for Friday if you want to. Why don't you try, do you want to try and like figure it out on your own first, or do you want me to help?
On your.
Okay, cool. Okay. So yeah, thanks everyone for calling in. I'll leave this open for the next half hour. But yeah, lecture's now over. Okay, people are having some file not found issues, so I'm just gonna show on my screen how you can make your file found. Okay, so what the notebook is looking for is for you to have copied things into your drive. So you should be in a place where it's my drive into a folder called Python for Physics. And then inside the Python for Physics folder, you should have the project and the data. If you're in a different folder, if you've named it differently, then you're going to need to change the file path to wherever you are. So my drive slash whatever folder you're in, if you're in another folder inside that one, slash whatever folder you're in. So you might have to play with the file path to get it to point to the right place. But if you go to your drive, you create a folder called Python for Physics and you put a copy of the code, so the code that you're going to edit in there, and make sure you put the text file in there too. It should run fine.
How if I cannot put it in day 4? I want to keep it in there, just edit the file path in the code.
Can they edit the materials for students folders?
Probably should, I assume Wyatt wrote that, because they should.
Right.
That would be general. I think.
So don't make a copy in the folder that's for everybody. Make your own folder.
Whereas we have like copy.
It's why it really sucks to use online Google Colab.
Well, you're also welcome to download the notebook, download the text file, and use it on whatever you want to use it. Yeah.
Yeah.
All right, guys, it's noon, so I'm gonna end it here. Are there any announcements? There will be another Reyes speaker about their research this Friday.
Yes. Yes, this Friday during the second half of the class, so at 11 a.m. PDT. There will be another speaker who will talk about the research much like Anna did today. So stay tuned for that. We will meet again at 10 in the morning on Friday, and then it'll transition smoothly into that speaker. Okay. So we'll see you guys on Friday, hopefully. Thank you for coming.
Thanks for calling in. Bye.